So how do we get from a Poisson process to a gamma? Well, if you recall from the Poisson process, we defined a so-called inter-arrival times or inter-event times, SK. And this is the time between the k minus first event and the kth event. And we saw that these are IID exponentials. So the arrival time, tk, is a cumulative sum. So tk is obviously s1 plus s2 up to plus sk, because we'll have these differences, and the so tk minus 1, that will be sk, and then we add to this tk minus 1 minus tk minus 2, and the tk minus 1s will cancel and keep going, and they will all cancel, and the only term that will be left is this tk. So what we want is the distribution of this tk. It's the sum of these exponentials, the sum of k independent exponentials. And this will turn out to be a gamma distribution with parameters k and lambda. So this is specifically the case of k being an integer. And so this gamma will represent the time to the kth event. Now we're going to use this identity or this duality, that the set of tk less than or equal to t is equivalent as in the underlying sample space to the event that nt, the number of events that have occurred at some time t, are greater than or equal to k. This is obviously true, right? Both of them denote the fact that by time t, k events have occurred. At least k events have occurred by time t. Now we're going to need the Poisson distribution at a fixed t. So at a fixed t, end of t is a Poisson random variable with rate lambda times t. Let's remind ourselves of what the probability mass function looks like for this. Well, we give it the symbol pkt, and it is defined as the probability that nt is equal to k. And it's given by this quantity here, this expression, lambda t to the power k over k factorial e to the minus lambda t. And so from this, the probability that tk is less than or equal to t, which has to be the probability that nt is greater than or equal to k. Remember, these are equivalent events. And that, what's this? Well, this is 1 minus the probability that nt is less than k, right? The complement of this event. 1 minus the probability of the complement of that event. And what's this? Well, this is the 1 minus the probability that n of t at some time t is equal to 1 plus the probability that nt is equal to 2 plus dot 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 up to probability that nt is equal to k minus 1, right? So it's a sum, it's 1 minus the sum of all of these. So I need to close this bracket here, right? Now these, so this is P1t, this is P2t, and this is P k minus 1 at t, the PMF. So we have 1 minus the sum from j equals 0 to k minus 1 of the PMF values. And this is equal to what? Well, from here, for if we put k equals j in here, we'll get this value, pj at t. So we've got 1 minus the sum from j equals 0 to k minus 1 of this sum here. We actually derived this using calculus, because what do we have here? We have the PMS, the CDF of TK, the cumulative distribution function. This defines the CDF. The CDF is defined as the probability at, so this CDF, let me call it F, t is defined as the probability, the CDF for tk, that tk is less than or equal to t. And it's given by this expression here. So we have just written down the CDF, which I derived earlier using calculus. So if we differentiate this, we should get the density. So let me call that density ftk. That's going to be equal to the derivative with respect to t of this CDF. So it's the derivative of this thing here, 1 minus this sum, which is equal to this quantity here. So why do we get this? We need to find d by dt. So the derivative of 1 is obviously 0. So what we need is minus d by dt of this sum from j equals 0 to k minus 1 of lambda t to the power j over j factorial e to the minus lambda t. So let's focus on this derivative, forget about the negative sign there. Let's write this out for a few terms. So for j equals 0, what do we have? We want d by dt of, so for j equals 0, we're going to have 1 over 1. So it's just e to the minus lambda t. And then we're going to have for j equals 1 lambda t over 1 e to the minus lambda t plus lambda t squared over 2 e to the minus lambda t plus lambda t cubed over 3 factorial e to the minus lambda t. And we keep going until we get to k minus 1. So let's differentiate the inside of this and see what we get. Well, differentiating e to the minus lambda t, we're going to get minus lambda e to the minus lambda t. Now this, we differentiate using the product rule, so we're going to get plus lambda e to the minus lambda t, and we're going to get minus lambda squared t e to the minus lambda t. Now this one here, what do we get from here? Well, we're going to get 2, and that will cancel this 2 when we differentiate the t squared. We're going to get 2, well, the 2 cancels, lambda squared t e to the minus lambda t. And then we'll get minus, so that's plus, minus lambda times lambda t squared over 2 e to the minus lambda t. And then this term here, we're going to get plus 3 over 3 factorial lambda cubed t squared e to the minus lambda t. And then we'll get a minus lambda times lambda t cubed over 3 factorial e to the minus lambda t. And we'll keep going. There are more terms here. So let's see what's going on here. Well, this cancels with this. This cancels with this. So plus. Lambda times that. So it's going to be lambda cubed t squared over 2 e to the minus lambda t. 3 over 3 factorial is 2. 1 over 2. And so we get this cancels with this, and this will cancel. And we'll keep going. And just the last term for k minus 1 will give us this. So for k minus 1, we're going to have lambda t to the k minus 1 over k minus 1 factorial e to the minus lambda t. So when we differentiate this, we'll get one term, the term that we get when we differentiate this part, and that will cancel with something from the k minus second term. And we'll be left with lambda, the derivative of this times this. So we'll be left with minus lambda times lambda t to the power k minus 1 over k minus 1 factorial e to the minus lambda t. And this is lambda to the power k times t to the k minus 1, which is what we have here, over k minus 1 factorial. And the minus, obviously, because we have a minus here in this sum, that will become plus. Right? And so we're left with this, which is precisely this thing here. So that is the PDF, which is exactly the density of a gamma, specifically an Erlang distribution, because we are assuming here that we have an integer k. So indeed, we do get pk is distributed according to a gamma with parameters k and lambda.